Okay, so today we're going to venture into the world of adding vectors by components. And I do need to let you know, it is a process. Okay? It does take us some time to be able to go through this process from start to finish. So what we're going to do, because there's no other real way to do it, we're going to jump into an example and kind of detail the steps as we go through. And as you kind of see in your notes, it's even labeled as step 1, do this. Step 2, do this. And we will follow that same general procedure for adding vectors by components. When do we need to add vectors by components? Anytime that we have vectors that are not parallel to each other. Okay, so we'd have to go through this process, which is how most things are in reality. So let's just take a quick read of our sample problem here. While in the vicinity of a feeder, a hummingbird moves along the following path. So we have 3 displacement vectors. Our first one at 30 centimeters at 90 degrees, 30 centimeters at 45 degrees above the positive x-axis, and 40 centimeters at 180 degrees. And you will notice this problem is already a contradiction to one thing that I've told you, just because not everything always follows the rules. What should be the red flag that we already have raised? Okay, well, the 180 degrees, okay, we've said that all of our angles are going to be expressed with respect to the x-axis, the closest x-axis. Now, in mathematics, do you often see where they express that as an angle of 220 degrees? Yeah. What would you do from that? Where would you measure from? If you had an angle of 220 degrees, where do you measure that angle from, right? From the positive x-axis, and then you would just go ahead and work your way around. In that case, that would put us into the third quadrant, right? Okay? So I want you to know, if for some reason you were to see it that way, that's fine. More often than not, we will see it with respect to the closest x-axis. So let's start with this. Our first vector, 30 centimeters at 90 degrees. For labeling purposes, let's call that vector A. Because I'm going to color coordinate things a little bit here. Okay, we have our next vector will be vector B. I'll put that in purple up on the board. And then our last vector in vector C. Now, just real quick, I want a quick visualization of these vectors before we break them down into their components. So 30 centimeters at 90 degrees. Where is that vector going to point? Well, it should point up, parallel to the y-axis, the positive y-axis. So for vector A, okay, we would, if we were to draw that by itself, vector A would be pointing in an upward direction. Okay? B, okay, 45 degrees above the positive x-axis. Well, that should be pretty simple. It's going to point up and to the right. It is also 30 centimeters, so the relative length of that arrow should be similar to vector A. And then 40 centimeters at 180 degrees. How do we draw that if we're just doing a rough representation? Be careful, 180 degrees. If we're to start from the positive and we're going all the way around, it would point to the left. Okay? Now it is 40 centimeters, so that arrow should be just a little bit longer. Why do I want you to have this rough representation? Because I want you to be able to see this when we go to calculate components, what they should look like. Okay? Now that's kind of a pre-step, if you will. Step number 1 really is we need to find all of the x and y components for all of these vectors. When we take a look at A, we need to find AX and AY. Now for this vector that is pointing up, this should be easy. And think about what we even just talked about earlier today. Do you have to do, for this problem, A cosine theta, A sine theta for a vector that's parallel to the y-axis? No. You can if you'd want to, but 30 centimeters at 90 degrees. So what's AX going to be? Okay, good. Along the x-axis, we have a component of 0 centimeters. What do we get for AY? 30. Okay, and it is pointing up, so we don't have to do any correction with that. Okay, 30 centimeters. Do we now have the components for vector A? Yeah. Okay, I'm going to skip over to the side for another one that is pretty easy. We'll go to CX and CY for a minute. Again, I'm trying to keep the colors similar here. So we're 40 centimeters at 180 degrees. What would CX be? We can all just say it. What would it be? Not 40 centimeters. Negative 40 centimeters. And negative y? It's pointing to the left. We should be able to identify with that by now. Okay? Look at how it's drawn. It's going to the left. It's got to be a negative x component. CY would be? 0 centimeters. Okay. Those two are pretty easy, right? Any instance where we have a vector that's parallel to either the x or y axis, I'm okay with you doing that. Just be able to identify which component is 0 and then which one has some value. Okay, the other one is vector b. So for bx and by, do we need to calculate those components? Absolutely. It's a nice clean angle, but we do have to do equation, so vector b times the cosine of theta for bx. What's the equation going to be for by? What's the equation going to be for by? Vector b times sine of theta. So then we can go ahead and do our pluggy-chuggy once we have that all set up. So 30 times the cosine of what angle? 45 degrees. And then 30 sine of 45 degrees. I know, using an angle of 45 degrees, that should make this pretty easy. But let's go ahead and check it. We should already be in degree mode. So 30 cosine 45. Okay. What do we get, Madison, when we round that to 3 decimal places? When you got it? 21.213 monkeys. 21.213 bananas. It is centimeters. Always make sure we're putting our units with it. Okay? Quick check. Should that be a positive x component? We didn't really draw it as the right triangle, but if we were to draw x first and then y, yeah, it would be going to the right, so we would get that. Okay? What should we then get for by? 21.213 centimeters. Okay, well, we can calculate it, or also understand that with an angle of 45 degrees, the x and y components should be equivalent values. Good check to do it anyway. That's what we get. So that's step 1. Okay? We need to solve for all of the components for each of our vectors. If there's only 2 vectors, we only have to get 2 sets of components. If there were 4 vectors, we'd have to get 4 sets of components. If there were 100 vectors, we'd have to have 100 sets of components. Okay? However many we have, we're going to find all those components. Bless you.
Thank you.
Then, as we had just done in our lab, and we are going to find what we call Rx and Ry, which are the components of the resultant vector. I'm going to do R in red. Okay? So let's set up the equation for this. Rx is simply going to be the sum of everything we have. Do we have an x component for A? Yes. So that would be AX. Do we have an x component for B? Yes. Do we have an x component for C? Absolutely. So however many x components we have, just list them out. AX plus BX plus CX for what we have here. So then let's go back to our values. Okay? What is AX? 0. Okay? So 0 plus, what's BX? 21.213. And what's CX? Okay? Negative 40. So let's go ahead and find Rx. Ziad, when you got a quality response, let me know.
Negative 18.787 centimeters.
Okay, good. 1, it should be negative, shouldn't it? Okay, with what we have, we got to make sure that should be the case. And then in addition to that, 18.787 centimeters, that's fine. And let's just go ahead and look very quickly back at what we had. Okay, we had a vector that takes us in an upward direction, one that goes up a little bit to the right, another one that goes left. In terms of the x components, okay, we're going to end up with something that is going to overall take us to the left. Okay? So having an Rx that is negative simply means the net result of adding everything together, the sum of those vectors is going to be something that takes us to the left. All right, we're going to do the exact same process for Ry. So Ry would be equal to Ay plus By plus Cy. Okay, what was Ay? Okay, we had 30 centimeters for that. So plus By, 21.213 plus Cy, which was 0. Don't you dare touch your calculators. What's Ry? 51.213 centimeters. For what we had seen visually, should this be something that takes us in an upward direction when we add everything together? Absolutely. There's nothing that actually in this problem that took us in a downward direction, so we should expect that to be some positive value. Okay? So that is the next set of steps. Okay? Find Rx and find Ry by summing up the components that we have. Now, these next couple steps are all kind of grouped together. We are going to use Pythagorean's theorem along with Rx and Ry to figure out what the resultant vector is going to be. It is going to be a two-dimensional, in almost all instances, a two-dimensional vector. So we're going to solve for the magnitude first, then we'll solve for the direction. Okay? I'm actually going to kind of skip over to something because I want to do this first as our check. At the bottom of the page, I've given you a coordinate grid. And I want to start with Rx. Is Rx positive or negative? Negative. So starting at the origin, I want you to draw the x component of this, just taking us in a negative direction. Don't really care about scale at this point. What's Ry going to be, positive or negative? Positive. So from that point, we are then going to go in an upward direction. So if we were to kind of hand draw this in, this would be our diagram. Oh, I'm sorry, not Ry. That would be our diagram for our resultant vector. So Rx, Ry, there's our angle. Why do I want you to do this as the next step? That visual is going to be very helpful to check a couple of things along our way. We will put together our final answer when we get to that stage. But I think that visual is always a good thing to do. All right. So Pythagorean's theorem, which I know you have gotten accustomed to using a squared plus b squared equals c squared. However, we're going to use the physics-specific notation for what we have. And when we take a look at this diagram, we need to solve for the hypotenuse, correct? So we're going to solve for r. If we remembered way back to what we just did in trig, even though it's going to look a little funky at first, we need to have the rearranged version of this. So r equals the square root of Rx squared plus Ry squared. And again, even though it's in different notation, is that just Pythagorean's theorem? That's all it is. And now that we know these values, well, this should be pretty easy to do. Notice how, though, I have placed some parentheses in here, and I want you to use them. Equals square root, open parenthesis, Rx squared, negative 18.787. So what do you think you're going to plug in for Rx? Just 18.787 squared. Why would we not plug in that negative? Now, your calculator, depending on the iteration of software that you have, some of them will calculate that correctly, some will not. And ultimately, we're squaring it, so is the negative going to disappear? And here's why I say use the parentheses and don't worry about the negative. Actually, it's twofold. But the first part of it is, one, it's not going to matter if we square it, it should take care of it. But with some of your calculators, if you were to do like negative 5 squared, just 5 squared then tax the negative on the front. Then it would give you an answer of negative 25, which is incorrect. And since you are smarter than the device you hold in your hand, we're just not going to put that negative in. And it doesn't matter anyway. Okay? So open parenthesis 18.787 squared plus are 51.213 squared. Close it off. And do me a favor. Plug that into your calculator exactly as you see it. Square root piece, open parenthesis, 18.787 squared plus 51.213 squared, close parenthesis, enter. I want you to get into the habit, for those of you that try to do things in chunks, to have some faith in yourself and plug it in one string. But it is going to reduce the amount of errors that we can make as a result of that. And Sydney, what do you get as your value for R?
54.550.
54.550 monkeys, bananas, gallons of milk. Centimeters are our units for this. Okay? Quick check, because we're all good at math. Should the hypotenuse be longer than the length of each of your legs? Absolutely. Is it? Yes. Okay? So, that is reasonable from that perspective, and that is what we should calculate it to be. 54.550 centimeters. Questions so far? I've kind of done a large chunk of things. All right, so then one more thing to do. We're going to use an inverse trig function to calculate the angle with respect to the x-axis. For those of you that remember when we're doing this, what would be the preferred trig function to reduce rounding error? The tangent in this case. Now, does that eliminate rounding error? No, because Rx and Ry's individual values are rounded to the thousandth place. But if we were to use sine and cosine, that incorporates the hypotenuse, which is another derived value that we also have rounded. So we reduce the rounding error by using the tangent function. So the rearranged version of it, theta equals inverse tangent of the ratio, but now we're actually going to use the proper values. What is the opposite side of this right triangle? Ry. Over, what's the adjacent? Rx. So inverse tangent of the ratio Ry over Rx. Now we can do our pluggy chuggy, inverse tangent of Ry, which I forget that was the 51.213, over the 18.787. And again, we are only going to use the value, not the negative with this. Because we kind of chatted a little bit about this in your lab. A negative angle doesn't make sense. Okay? And to even throw things even further, if you're in, let's say, the second quadrant, in pure calculation, if you plugged in that negative value, it would give you a negative angle. One, that doesn't make sense. But then to doubly confuse you, if you were to do the third quadrant, where they both would be negative values, it would give you a positive angle. And again, that from a positive and negative standpoint, that just doesn't work. So when we plug in Rx and Ry both in the Pythagorean theorem and for the calculation of the angle, just use the absolute value of what that quantity is. And the negative does not help us or hurt us in terms of that calculation. Okay? So who's got a quality angle for us here? Zion?
69.855 degrees.
69.855 degrees is Zion's response. How many of you, by show of hands, would agree with that response? Good. We should. And Zion gets a nice big smile. A sense of accomplishment. Good job, buddy. Okay. All right. So good. Now we've done all the legwork. Now our final task is just to simply state our answer. And this is going to be the longest answer you've ever given to any mathematical problem in your life. More than likely. Okay? So, here is your answer. Your resultant vector is equal to the magnitude that we solved for with Pythagorean's theorem, which if we rewind to the slide, this is our 54.550 centimeters. Now, to continue using our terms from 2 classes ago, that is just the magnitude. We do not have a direction associated with that at the moment in our answer. So, magnitude at 69.855 5 degrees. In this case, above the negative x-axis. And please do me a favor. Circle or box that as your final response. So let's use our lens of checking things on our response. Do we have the magnitude of that resultant vector? Yes. Do we have a very clearly defined direction with that vector? Absolutely. So that's what our response is going to be. Now with these problems, I fully understand I'm not going to give you 30 of these problems to do for practice. Okay? I'm mean, but I'm not that mean. Okay? But as we go through, we should be able to follow this as a practice for any type of problem with vector addition. Okay? So here's what I want to do. I just want to do a quick recap again, just so we kind of understand everything from the very beginning. However, step number 1, however many vectors we have to find all of their vector components. Now, if they're all at odd angles, then we have to do for every single one cosine theta, sine theta to figure out what they're going to be. If they're parallel to an axis, it does make our life a little easier. Then we need to find Rx and Ry by summing up all the x components, summing up all the y components. I'd highly suggest once you get that, draw the correct diagram so you have a good visual to reference. Pythagorean theorem, inverse tangent, and then our final answer statement. That's a lot to process, and sometimes in physics, I just have to put this out there. Sometimes I have to kind of give you this big process, and sometimes that's just what we have to do. Okay? What I'm going to ask you to do now is flip your page over. And what you will find is sample problem B. I would like for you, from start to finish, I want you to carry out this problem. Look at all the space you have. You have plenty of space there. Okay? So you can flip back and forth. Use the front of the page as your guide. Okay, step number 1. Here's what I need to do. Figure it all out. Okay? As you can kind of see, even though they're all angles of 60 degrees, we have a lot of components to calculate. Okay? And then walk yourself through the process. I will give you a solid maybe 10 plus minutes. But I want you to work through this on your own from start to finish. Sound good? All right, let's rock and roll. Okay, for those that are ready, I know it might be a little difficult to see on the board. You can go ahead and check your response. Please do not cheat yourself. Make sure you have it solved before you check. If you do not walk through the process yourself, you're not going to learn the process. Okay, so if you're not ready to check your full and complete response, then you're not ready to view what's on the board. Okay, but if you are, check what you have. If you feel like you're all good, you can go on to the last thing, which was the 4 problems that are in our problem set. They're going to be due for next class. Okay, so I think most of us, okay, once we kind of check with this, probably should be good. If you have questions, by all means, we'll make sure that we address them before we go.